All right, 6.2 concentrations of solutions. So now we're going to determine the strength of the solutions that we've been talking about so intimately over the past week. So solution concentration. We're going to measure solution concentration the following way. We're going to do so by looking at the moles of solute divided by the liters of solution. And if we compress that, that's going to turn into moles per liter. And that actually has a name. That's called molarity. Now, my group, we talked a little bit about molarity in first semester. If you're an even center, I think you've talked a lot about this. Everybody else may not have talked about it yet. So we'll have a nice refresher here. We're going to abbreviate molarity with a capital M. And if we were looking for, say, the concentration of a specific substance, like the concentration of sodium chloride in solution, we can abbreviate that with some brackets. So when you see these brackets around a particular compound, like I've got here, that just means the concentration of NaCl. And to get a little bit of closer look at what concentration actually means, I've got two different substances here in volumetric flasks. The one on the left is a concentrated solution, and the one on the right is more dilute. And if you'll notice, the molecular level diagram is showing that the one on the left has way more solute particles than the one on the right. The one on the right, you can actually see way less solute particles and more solvent particles. And so that's what really creates that differentiation between the concentrated and dilute solutions. So the image here is really kind of a nifty one because it breaks down what concentration truly means for different phases of substances. So if we start at the top, we've got like a solid substance. I just took bars of gold. And it doesn't matter what size bar of gold you have, essentially the molarity of that is always going to be the same. So molarity doesn't change for solid substances. And the same thing can be held true for pure substances. So if you've got like pure water, the molarity of pure water doesn't change. There's no real solute. It's just one substance that we're talking about. So molarities really come into play when we're talking about like gases, for instance. Or when we're talking about solutions, or maybe gases dissolved in solution, because there we have a particular solute molecule. In the case of the bottom diagram here, the solute molecule is the NaCl, and you have a solvent molecule, which in the case of this one is the water, is H2O. On the right side of the page, you can see these goofy-looking flasks. They're called volumetric flasks, and this is kind of a neat representation of the difference between concentrated and dilute. The material on the far left is super concentrated, the material on the far right is super dilute. So really, at the end of the day, it's not really a difficult concept, especially when you're working with compounds that are colored. It's even a visual concept that we will take a little bit closer look at the lab next week. All right. So let's get into some calculations then. We're going to take a look at a solution, 150 milliliters of a solution that contains 18.3 grams of the solid copper 2 chloride. And the question here is to look for the molarity. So again, molarity is concentration. What we want to put a number to that molarity. So what we're looking for is the moles of copper chloride per the liters of solution. Now copper chloride has a molar mass of 134.45 grams per mole. Now typically when we're doing molarity problems, finding the molar mass of the solid, which is usually the solute that you're working with, is crucial. So you might as well go ahead and find it right away. So how do we set this up? We're going to start with the 18.3 grams of copper 2 chloride. We want to get that into moles because, as my red text says, we are looking for moles of copper chloride. So that's why we're doing this initial step right here that I've highlighted in purple. Now finally, we want to be able to be left with liters of solution, or at least that's what we want on the bottom of our fraction. So we have to make sure that we take 150 milliliters and we convert it into liters. For those of you not really comfortable with your metric conversions, that's just dividing by 1,000. So that'll give us liters of solution, and that's what I'm doing in the green box here on the right side of the page. So at the end of the day, if we look at our cancellations, our grams are going to go away. And what are we going to be left with? Well, we're going to be left with moles per liter. And by definition, on that last slide, folks, that's what molarity is. That's moles per liter. So if we do the calculation appropriately, this solution has a concentration of 0.907 molar. It's usually how we represent the concentrations. We use the word molar instead of molarity. One more example problem. Now we just want to determine the sodium ion concentration in 500 milliliters of a 0.25 molar sodium carbonate solution. All right, so let's walk through this one. The first thing that I notice here is that sodium carbonate is given in words and it isn't given as the formula, so I'm going to go ahead and write that. All right, that's going to be Na2CO3. That's my sodium carbonate. That's a solid. Now let's pretend that I break that apart into its individual ions. Well, sodium is the cation, it's the metal, and how many of those do I have? I have 2 of them. That's what that subscript means. So let's say I were to put this into some water. I would have 2 sodium ions, so 2 Na. Remember they're 1 plus, that would be aqueous. And I would have 1 carbonate ion, 2 negative, and that'd also be aqueous. So what does this tell me? Well, this tells me that for every 1 mole of sodium carbonate, I'm going to generate 2 moles of sodium ions. And that's going to be really crucial in me developing an answer to this problem. So we want to remember that ratio. That's a 2-to-1 ratio. All right, let's go ahead and attack this problem now. We have 0.25 moles per liter of the sodium carbonate solution. That's the concentration. All right? We want to figure out what the sodium ion concentration is. Well, here's what we know. Remember, this is for Na2CO3. Okay? We know that for every 1 mole of sodium carbonate, we are going to produce 2 moles of the sodium ion. Again, where does that come from? Well, it comes right here from that ratio. That's a 1 and a 2, and that came from the subscript. So if we do our math correctly, we're going to have the moles of sodium carbonate are going to cancel out. 0.25 times 2 is going to equal us a 0.50 molar sodium ion concentration. And that's our final answer. So the number up here that gives us the volume is actually kind of a detractor number. It's one that we actually don't need in the equation. All right, so that's concentration and molarity.